Okay, so before we start, let us discuss a bit about the topics that were covered right after recess week, I think, which is about network address translation and also some about routing protocols. So network address translation is basically as a router, you are trying to somehow hide out whatever is within your local IP address, so that this will be like the interface within your internal local network. Okay, so each interface they have IP addresses that are provided in the reserved range. For example, if I have a subnet mask of 10.0.0.0.8, then this corresponds to 10.0.0.0.0 all the way to 10.255.255.255. Okay, so this one is like just normal subnet mask items. But now as a router, what I want to do now is I am some kind of a gatekeeper that keeps all the IP addresses within my local network. Okay? So I represent like some kind of, in the UN General Assembly, one delegate will represent one country. So this delegate is similar to your router. Okay? This router will represent all of your local network. However, it must still keep a certain mapping. That means each local IP will now be mapped to an external port, which is a port on your router. Okay? And hence, different hosts on the same local network will have the same external IP address, but they will have a different port on the router. Hence, the router will also need to store the NAT table in memory. So this is an example of the NAT table. It stores, for example, this is a host inside your local area network, and this host will correspond to, after it passes my router, this will be the new IP address I assign to this host, and this will be the new port, so that whenever something comes here, I know that it should be redirected to this local host on the local area network. Okay? So as a router, all you need to do now is, for example, I'm the router here. There's a local host sending an item. When this local host sends me the source port, the IP address, I will now have to change all of that IP address and all of that port down to whatever I assign them with my table. Now, once I assign them, I will have to remember the mapping. And once anything comes, any mail comes through me, I will have to replace the external IP address to my internal IP address, then I send to the host. Okay? So that is essentially the network address translation table. Any questions? No? Okay. Then, we also learned about IP datagrams, which is essentially adding much burden to understanding your TCP header stuff. So we learned that IP also have their own headers, and combining IP header and the data that was sent from the transport layer, we now have an IP datagram. So IP datagram is this is like containing the header and data, and this can be split according to the MTU of the links. What is MTU? It's not Malaysia Technological University. What is MTU? Maximum transfer unit. Okay, MTU is provided by the link layer. It's basically saying, as a link layer, how much can I hold in one point of time? That is basically your MTU. If I want to send one segment, what is the largest size that I can send inside my link layer? Okay, that is the MTU here. So new headers, they are added to each smaller part. If I want to split down a huge IP datagram down into smaller datagrams, then I will have to include each IP header inside the smaller datagrams also. Can anyone tell me what is the process of splitting the larger datagrams into smaller datagrams? It's in the slide also. Fragmentation. Okay, fragmentation is when you want to split a huge datagram down to smaller size fragments. Any questions? We are going to see fragmentation soon also. Okay, now when you do fragmentation, there are two items that you need to keep track of. Actually, three items, sorry. First one is the identification field. This will be the same as the original IP datagram. Okay, the ID should be the same. Second one, there's something called a flag here. So the flag, it tells you whether the fragment itself is the last part of that IP datagram or not. Okay? So if it's not the last one, we put 1. If it's the last one, we put 0. And finally, we have the offset. Offset tells you the first byte number. However, this is provided in the multiples of 8 bytes, not 8 bits. Okay? So that means, for example here, if my header is 20 bytes, and my payload is 480 bytes, then in that case, the first datagram here, the small fragment, it will contain byte 0 to 479. Then the second one will contain 480 to 959. Yeah. And the third one will contain 960 and onwards. Okay? So in that case, the offset here is basically what is the first byte that will be sent in sequence. Hence the offset will be 480 divided by 8 bytes. That is your 60 here. Okay? So you can think of it similar to like a sequence number in a sense. But the sequence number divided by 8. Any questions? No? Okay. Okay, no questions. We move on to tutorial questions today. First one is we consider the network setup in the following figure. Suppose that the ISP assigns the router address 24.34.112.235 and the network address of this home network as 192.168.1.0 up to 24 bits. So the first question, can we give an example IP address assignment to all interfaces within this network? So there are several arrows here that we need to fill. First one is this arrow, second one is this arrow, and third one is what can be assigned to each of these hosts within this network. Maybe let's start from this point first. Can anyone tell me what is this value? The leftmost. So if it's the leftmost one, which side is the router facing? The external side or the internal side? If it's the left one. External side, right? So in this case, if I'm the router, this is the external facing side. So what will be the address of the external facing side? Which one? The WAN address, right? So this one, the ISP assigning the router address 24.34.112.235. This should be basically the external identifier of your router. Okay, thank you, Heiko. So this will be the external identifier of your router. Anyone who wants to contact this router will have to contact 24.34 all the way. Any questions? Today's class seemed quiet. Okay. Now, how can we assign whatever is inside them? How can we assign this? We use a private IP. So how can we assign? Actually, any random numbers within that subnet mask should be okay. Okay? However, the catch here is we have to assign one additional address to your router. Or else, your host now doesn't know where to contact if I want to contact external parties per se. Okay? So in that case, you have to assign one additional address now for your router. Any questions? Technically you can, but we can reserve that for the callback address also, if you want. Technically can. Actually, if you see the tutorial solutions later on, you will see that it's actually 259, something like that. Basically, anything that falls within the prefix should be can. Okay, if no questions, now, suppose that each host has two ongoing TCP connections, and all of them are pointing to port 80 of the server at 128.119.40.86. How can we map this out in the NAT translation table? Actually, this one is very random, I guess. This one is very random. Anyone? Okay. How many port numbers can we use? Or how many should we use?
6.
Okay, we have 6 port numbers now. It's port number 1, 2, 3, 4, 5, 6. Then, what can we say about these IP addresses? Say this is the WAN side, and this is the LAN side. Okay, we use the external IP address here because technically this would be the identifier of when it passes through the router. This should represent the whole local area network. Okay, then the port numbers here will be different. Say this will be port number, say 1000, 2000, 3000, all the way to 6000. Okay. Okay, now the WAN side is okay. How about the LAN side? Okay, so this will correspond to the private IP. Say this is host 1, host 2, host 3. However, since one host will have two ongoing connections, these two IP addresses will be the same. However, the port now will be different. Say this will be port 2105, 2106, something like this. Okay, then now we already have the NAT translation table. So something like this. You'll see that these are basically host A, host B, host C, for example. Okay, I think my example is not consistent, but yeah. This host A, host B, host C, each of them will now have different ports to cater that one port will handle one TCP connection. Now, this different connection will correspond to a different port on the WAN side, but the IP addresses here should be the same, which is basically the external IP address of your router. Okay? Any questions? This one is quite random, like you can assign any port number you want actually.
But we can't use port numbers below 124.
Yep. So yeah, this should be wrong. Any questions?
I don't understand
Mm-mm.
how we did.
Okay. I think
Port
okay.
2105.
How does the sorry?
How does the, for example, data from the website know which host to use?
Data from the WAN side. Okay. So for example, let's say I assign you are this one, the 192.168.1.2.2105. Okay. Now suppose if I want to send to you, for example, you send data to me first. Okay. When you send data to me, initially your source number is the 192.168 stuff. Okay. Then when it passes through the router, okay, this is you. Then for example, there will be another person, say Raj will be the router. Now when you give the message to Raj, Raj will change your address down to this thing. Okay, down to this thing. Then when I receive that item, I see that your source address is already this item. So when I want to reply to you, then I'll just send this item. However, the unique thing is this NAT translation table is actually a unique item. So per se, there should not be two different hosts that will connect to the same website. So when I send my item to this website only, I give to Raj, Raj knows that this is heading for 5000, then it will send to you. Because this port number will be unique for each of the LAN hosts. Okay? So it's like, this is like anonymous identity per se, but it should still be unique for the router to address. Okay? Does that answer? Yeah, okay. Now, we move on to question 2. Consider sending a 1500 byte IP datagram into a link that has an MTU of 500 bytes. Suppose the original datagram is stamped with ID 422 and also assume that the IP header is 20 bytes long. How many fragments will be generated? Who says 3 fragments? 4 fragments? 5? I don't know. Okay, why 4? Okay. Yep. Okay.
Right? Well, technically, you divide into 4 fragments, and each of them will have like an extra fragment.
Okay, so we divide this into 4 fragments. Why can't we divide this into 3?
Because need the header for each of them. So there's an additional 60 bytes.
Exactly. So if you happen to divide this by 3, then you will get something around 490, right? Yeah, you will get around something like this. If you add the 20 bytes header, this will become 510 about like this, and this will exceed the MTU. So you have to divide this by 4 fragments. Okay? Yep, so this will be 4 fragments. Easier way to visualize this, as what Marisa mentioned, you have this original datagram, but this datagram itself is actually part of 1480 for data, 20 bytes of header. So now let us take the header of the equation. We now want to split your 1480 into different fragments. How can we split that? This is one fragment, two fragment, three fragment, and this is the fourth fragment. Why do I split it 480, 480, 480, 60? So that when I combine with the IP header, this will still be part of the MTU of 500 bytes. Okay? So my goal is, if I fragment it out together, once I combine with the IP header in the end, this should not exceed 500 bytes. Hence, the data should not exceed 480 bytes in this case. Okay? So, since 20 bytes is used for the IP header, then the original data in your original datagram is only 1480 bytes. And the maximum size of data we can send for each tiny fragment is equal to your MTU 500 bytes minus the IP header 20 bytes. So you can only fit 480 bytes of data within each tiny fragment now. Hence, we need to split this into 4 fragments, which is taking the ceiling of 1480 divided by 480. Any questions? Yep. Should be 40, yeah? Yeah, should be 40. Okay, yeah, should be 40. Okay, I'll change this later. Thanks for informing, yeah. Okay, should be 40 years. Okay. Okay, next. Wow, this will change a lot of my slides. Okay, what is the length of each fragment, including the IP header? Yeah. Then technically this should be similar to just now, yep. So this will be 480 plus 20, 500, and this should be 40 plus 20, which is 60. Okay? Yeah, I copied the wrong one. Yeah, so the length itself, the length of each fragment, including the header, will be basically just now, this item 480 plus 20, 480 plus 20, 480 plus 20, and finally this should be 40 plus 20. Okay? So that will give you this 500 plus 500 plus 500 plus 60. So from the original 1500 bytes, we will now convert this into 1560 bytes because of the additional 3 headers that we have to include. Okay? Any questions? No? Okay. Now, what are the values of the ID, offset, and the flag in each fragment? Okay, for ID should be all the same. That is 422. How about the offset and the flag? Maybe the flag first. I think flag is easy. 0001? 1110, okay? So the flag is basically 0. That tells you that this is the last fragment, okay? So the flag will be 1110. How about the offset? Okay, maybe let's see. So ID number is correct. This should be the same among all the fragments, which is similar to the original ID. Then the flag itself, 0 if it's the last fragment, 1 if it's still continuing. How about the offset? So for the offset, right, the way I usually do it is it's easier for me to look through what is the first byte of each fragment. Since the first one has like 480 bytes, and this is the initial one, so the first byte is 0. Second one, it starts from 480. Third one starts from 960. Then fourth one will start from 960 plus 480. Now, since I already received the first byte of each fragment, then I can just divide this by 8. I will get my offset. Okay? So the offset is just basically, what is your first byte? Divide this by 8. Then now we have the complete table with the full ID, offset, and the flag. Any questions? So if you need to look this at a better view, the way how the module addresses, It's similar to this. This will be the original IP datagram. Now, once you fragment it out together, then this will be the different fragments. Okay? Any questions? Now, if no questions, we move on to the fun part of today's tutorial. That is routing algorithms about counting the distance factors. Okay, so routing algorithms. Which algorithm do we use for doing the routing? The distance factor, yeah? With which certain algorithm? Bellman-Ford, okay? So we are not going to use Dijkstra, but we are going to use Bellman-Ford, unfortunately, for this. Okay? So we are going to use Bellman-Ford for updating the distance factors. So given this diagram with a simple network topology, 4 nodes are there. The links in the diagram are labeled with the cost of each link. Now, once the protocol has terminated, and each node now knows the cost of the minimum path to every other node. We want to fill out this distance table. So how can we fill this? Anyone has tried this? I think even you try normally, I think should be quite fast to get. But it's also important to understand how the iterations work, because that is the final exam question last year. They will ask you after like 2 iterations, what is the distance factor? Yeah, so it's important to know how the distance works. Okay, so for this we can actually use the Bellman-Ford algorithm. But first of all, we have to see how the table looks like before any iteration is actually done. In short, on how the module teaches is more like the difference of Bellman-Ford in this module and the normal 2040 module is for this module you are trying to change it to different views. Okay, if for like 2040 is only starting from one source, how can you get all the other costs? But now we are trying to see this is from one source, then what if I change the source to this one? Then I change the source, Then I repeat all the way until no one is updated anymore. Okay, so that is the main change in this module. Okay, so I guess first one is actually, let me just draw the diagram on board here. Say we have W, X, W, X, Y, and Z. W to Z, W to, yeah, this thing. This is 20, 2, 6, 7, and 3 and 3. Okay. Okay, first one is if I want to compute the cost, this one is quite easy. Basically, I just need to iterate through all the single edges here, then I update my table accordingly. Okay, so this is the table right before I try to compute Bellman-Ford. Okay, initially say on X, if I want to go to W, what X can see now, just from that position without consulting any other views, is basically just X to W is 3, X to Y is 3, and X to Z is 6. Okay, just basically if I look through here, without knowing that all these other paths exist, what is my initial distances? Okay, I think this should be quite easy, right? Okay, any questions for the initial distance factor? This was before any iteration is done. Okay, now once this is done, all I need to do now is to try to update. Okay, once I try to update here, say for example, if I want to compute the distance from X to my Y. Okay, the distance from X to Y here is equivalent to saying, for all of my neighbors, my W, Y, and Z, what is the cost for me to go there, and the estimated distance from this W all the way to Y. For example, okay? So basically this thing is showing, for each of my neighbor, W, Y, and Z, I want to calculate the minimum of going from X to that neighbor, and from that neighbor all the way to Y. Okay? Assuming that this will be fixed in the upcoming iterations. Okay? So this is basically your Bellman-Ford algorithm here. For each time you try to rex them, that is basically from X here, go to W, find the distance from W to Y, from X to Z, then Z to Y, and then from X to Y, then from Y to Y. Okay? Then that's the time I will get, this is 3 plus 7, 3 plus 0, 6 plus 2. Okay? However, do note that when you want to compute the dwy, dyyy, dzy, that's the time you use the table. But if you want to compute the cost, you use the graph. Okay? Don't mix this around, basically. So for x itself, you will get this kind of computation. Just now, the first iteration, you will get the distance from x to y is unchanged, still 3. From x to w is 3. However, now from x to z, instead of going this directly from x to z, I can go from x to y first, then my distance of y to z is just 2. So I'm taking, basically what I'm doing now is I'm going from x to y and I take the shortest path from y to, for example, z. Okay? Hence I will get, when I update this 6 now should be changed to 5 instead. Okay? Any questions? Clear? Confused? Yeah. So basically, yeah, it's more of a normal Bellman-Ford algorithm just for the x first. Okay? So the shortest path from x to certain node y is the cost from this x to every single neighbor plus the shortest distance from that neighbor to this y. Then we find the minimum. Any questions? No? Okay. Then maybe before we proceed, can anyone give me what is the value of this y table after the first update? Once x has been updated. Can anyone give me this row for y? Anyone? Six three zero two. Why is the first one changed to 6? Okay, y can go to x first before going to w now. Because we already have like the distances from x to everywhere else. So now I can assume this way. Initially from w to x, this is the cost would be this would be 3, this would be 2, and this would be x to w, y to w is 7. Yeah. So this is the cost that w sees. However, given that we already filled the table in the first iteration, now we have what is the shortest distance from x to w. And the shortest distance that would be 3. And this would be z to w. This would be 20. Okay? So after the first iteration, I will see, once I take this all, I will find the minimum. Minimum of 3 plus 3 plus 7 plus 0, 2 plus 20. Then I will get that this is the minimum. I will have to update my table accordingly. Okay, so this is just for one cell. You repeat this for all 3 other cells. Then you will get this item. For node y, when you try to update this, y to w will be updated to 6, y to x will still remain 3, y to z will still remain 2. Okay? Any questions? I would assume this will come out on finals. Questions? No? Okay. Then we thought lots of generality since it's difficult for me to plot out every single iteration. So this is how the final table should look like. Basically, you repeat from x to y to z, then you try to repeat one more, see if there's any update done. If no updates, then that should be the final table already. Okay? Any questions? Okay, if no questions, now let us do a very quick one on this Wireshark item, which is basically demonstrating ICMP. Anyone knows what ICMP stands for? The I is for? Ayo. Internet? Control? Message? What is P? Protocol. Okay? So ICMP is Internet Control Message Protocol. Okay, how is it used? Basically, it's used for communicating your network level information. Okay, try to look through the lecture slides also on this. I would assume this will come out on the multiple choice questions. I don't think this will be an essay question. Okay, but right now, we want to try to use Wireshark for this. So, first one is as usual, we go to the capture options. Oh, sorry. My bad. Okay. So as usual, we go to capture options here. Select whatever is your Wi-Fi, then you start. Okay? Then continue without saving. Okay, now that means now my laptop is already starting to capture any packets that is going out and in of my laptop. Then all I need to do now is to try to ping. Okay? To do that, I can just go say ping www.google.com. So what ping does is it tries to send, say, a certain amount of data to this google.com. Okay? To check if the server is alive or not, in a sense. Which actually I tried doing to my website, but seems like it doesn't work. There's a timeout there. Probably because it's like static or some sense. Yeah. So anyways, once you're done with that, you can actually go to the display filter here and type out ICMP. And once you've done so, this will be basically filtering out all the packets that uses the ICMP protocol. Okay? You will see that for the first 8 packets, it's basically request and response. Whereas for the last one, since the request timeout, so it's only all requests. Okay, so first question. Within this IP header, what is the value of the protocol? The upper layer protocol. In that sense, you just need to double click on this. You see the IP version. Now you will see this is your protocol, which is an ICMP protocol. Okay? Now, the next question in this question 4 is asking from one datagram to another, what will be different? What fields will be different? Anyone? I ping 4 times, right? The ID will be different. Because the ID is different, the checksum will be different. Okay? So let's try to see here. My ID here is 15017. Then if I go to another request, now this will be 15018. Then this should be 15019. Okay, so the ID of the datagrams will be different. And hence, because the ID is part of the header, the checksum will also be different. Because the header can corrupt anytime. So the checksum will compute every single thing. Okay? Any questions? Yeah. If not, then you can try to do this, especially those interested in security. This will help in your CTF assignments. And if not, then that'll be it for today's tutorial. So if you have any questions, feel free to ask, or else please scan the QR code to confirm your attendance. Thank you.